So, hello again. Thank you for coming. I'm Alexey Aristov, and I will speak today about OTP-like, our approach towards OTP-like processes and behaviors for Clojure, based on our experience from Erlang. Unfortunately, my pointer is slightly hopeless here, and I will have a lot of code. So I will try to somehow point the upper side of the code, lower side of the code, and so on. Pointer doesn't work. I'm very sorry for that. So first of all, I will start with a little recap of core.async. Who here in the audience has an experience with core.async? Oh, almost everyone. Cool. So then it will be short. So core.async is a very good basis for asynchronous programming in Clojure and even in Clojure script. It provides you with lightweight processes, Go blocks, which in case of Clojure are implemented. They run on top of thread pool executors. It provides you with channels which can communicate, which allow communication between Go blocks and exchange data. It has a lot of useful primitives, just some of them. You can do publish, subscribe, you can do tap on tap, basically to broadcast messages. Other thing, you have alts and so on. It's a very good thing. Actually, we used it a lot for different applications. But unfortunately, or fortunately, it's not that bad, but it's just how it works. It's slightly too low level. I mean that you have to take care of a lot of small things to get your application working reliable, stable, and so on. This is a short example which will demonstrate into what kind of problems you may run if you are not very careful with core.async. I have two code snippets. They're visible pretty well, yeah? On the left side, I have a producer, which does nothing else than places some data on channel recursively. And on the right side, we have a consumer which reads this data from the channel, processes it, and loops again. So what are the potential problems in this code? First of all, you can easily basically lock the whole system by crashing the right side. Imagine if our process function throws an exception, and this Go loop terminates forever. Our producer will work for a while, depending on the channel behind it, then some back pressure will get applied, we run out of channel, and our producer will stop. It will never know that consumer just crashed. It's also a little bit unclear who owns the channel, basically where to declare it, should it be disposed together with the consumer, or maybe with producer. What if there are several consumers? It's easy to run into a mistake when you start to consume, and two consumers start to consume from the same channel. Sometimes this is what you want, sometimes not. It's just a question of a lot of small cases. I'm not talking about timeouts here. Yes, we can easily implement timeout handling. What if consumer doesn't receive a message within a certain time? But here it grows and grows and grows in code. You have to add a lot of small things to get your code properly done. Or you have to build some sort of framework, some sort of structure on top of core.async. So we did, but because in our company we have a significant, if not say big, experience with Erlang OTP. Who has Erlang OTP experience? Slightly less, but still. We decided, okay, why to invent something on our own? Let's better reuse some ideas from Erlang and try to apply it to Clojure and core.async. So it's a functional language. We are on the functional language conference, so it's nothing new for us. It has lightweight processes as building blocks. It's not based on JVM. It has its own very specific virtual machine with soft real-time properties and so on. But all in all, it's a functional language with lightweight processes. It's an old thing. It was developed in '86, I think, first release. So it has a lot of experience behind it. And there are many proven design patterns which can be reused, and they're tested with time. It has built-in distribution features. It means you can send messages between operating system process nodes. We're not sure yet if we're going to implement it in OTP-like or not, but at least it has it. And it has just a small snippet for those who haven't seen. It's arguably, but some people say it's a little bit weird and strange how to write in it. Yes. So what is OTP-like? It's a simple, pure Clojure library. It has basically two major dependencies. It depends on core.async for asynchronous operations for channels and Go blocks, and it depends on core match. You know, in Erlang, pattern matching is a very important part of the language, so we use it also very actively. It emulates a small subset of Erlang OTP features, not everything. I think we discussed it recently, maybe, I don't know, we cover 2-3% of Erlang OTP. It's in no way a replacement for Erlang OTP, out of very clear reason. It's another virtual machine. Basically, it's no chance even to try to approach Erlang within Java world. So it's not a replacement, it's just an idea how to reuse certain patterns. So from now on, I will start speaking about OTP-like itself, no more introductions. OTP-like, as Erlang introduces a concept of process. Basically, process is a Go block with attached inbox. It's slightly more than just a channel, actually it's two channels, but logically it's an inbox, and some control structures that handle certain things, which we'll discuss later. It's definitely possible to send messages to process. Any Clojure term can be a message. Processes obviously can receive and handle these messages. Process definition, let's say presentation-wise, it looks almost like a normal Clojure function definition. You start processes with OTP spawn function, and familiar with these functions. Every started process is identified by its process ID. So once you spawn the process, you get back a process ID, and then you can reference this process. For example, you can send messages to this process. It is possible to register process under a global name, in the global namespace, with all magic around it, that, for example, when process terminates, it gets automatically unregistered. So you can address processes not only by process ID, but with a global name. Yes. So here is our little example of OTP-like process. For the first example, I included also some initial declarations. We require OTP-like process namespace, refer some of the symbols. Then we have a proc-def statement. We define a process, name it hello world. Inside this process, we do nothing else than receive a message and print this message. That's it. And then we spawn this process. We use process spawn function, pass hello world to it, receive process ID back, and use a ! send function to send the hello world message to the PID. Our process will receive this message and safely terminate. It's the most primitive thing you can do with OTP-like, but it demonstrates how processes look. Let's now take a closer look at how process definition looks, what's in it there. So that's already an extended version of it. We have receive. Internally, receive is basically a pattern match structure based on core match. It consists of pairs of pattern and some code to do. So this process can receive message, two types of messages. One message is tuple or vector in case of Clojure with keyword print as the first element and some message as a second element. And in this case, it will print this message and recursively restart receiving again. And it can receive an exit message with keyword exit, which just returns, basically terminates the process. Additionally to that, we have to notice that, like in Erlang, if there is no appropriate match, appropriate pattern, the process will crash and will cease to exist. And we added a timeout feature, which is very important, so you can optionally add after and then some timeout in milliseconds. It means that if no message arrives within this time, the timeout handler will get in. In this case, we simply print receive timeout and restart everything recursively. So this is our process definition together with pattern match. Next. process on their own is very nice, but we want to handle them somehow together. Erlang provides a very, very extremely important concept called process linking. What does it mean? Actually, linking is a special connection between two processes, which has the following property. If one of these processes crash, exit, another one will do so as well. We have it in OTP-like. What is important? Linking is bidirectional, so if process A is linked to process B is automatically linked to process A. This operation linking is atomic, bidirectional, and it is very important for error recovery and supervision. I will speak about it later. Actually, the idea is that you group several processes which are somehow related together. If one of them crashes and perhaps leaves something in an inconsistent state, it's quite important to kill processes around it, which also may be a little bit confused and inconsistent. So it's a way to clean up. In Erlang world, there is this idea of early crash, early fail approach. So let's take a look at the linking example. So here we have two processes, process 1 and process 2, and a small snippet of code which does something. Process 1 is very simple. It starts, spawns another process, which is process 2, receives a message, passes message as is. Basically, process 1 can handle any message, passes it to the process 2, and recursively continues. Process 2 is slightly different. It can accept only messages of certain structure. Again, our tuple, our vector of message, keyword, and something, and prints the message. And now we spawn process 1, process 2 gets spawned automatically, and we send an unsupported message to it. Process 1 is still okay, passes message to the process 2, process 2 crashes, but because here we use spawn link function, before we use spawn, here it's spawn link, these processes get linked together, and process 1 will exit as well in case of such a error. So after we run the snippet, after some timeout, I think things are asynchronous, both processes will die. Pardon?
Why is the second receive?
It's a typo. Typo. Sorry. Yes. Of course, you can do it you can link processes with using spawn link function, or you can do it somewhere on the fly. There are link and unlink functions which can be used to build quite more sophisticated combination of that. Next example, trap exit. Every process has certain number of, let's say, attributes, flags, and so on. I will not speak about all of them. I will speak only about one. It's called trap exit. There's a function called process flag, which allows you to send a flag named trap exit. Here we set it true. What does it mean? Trap exit flag allows process to convert exits to regular messages. It means if I have two processes which are linked together, one of them has trap exit set to true, second one crashes. In this case, the first one, instead of being killed, let's say automatically, will receive a regular message of some predefined structure which will notify that his neighbor basically crashed. And here we have an example. I skipped process 2 from the previous example. It's just the same code. We start process 2. We are trapping exits. We receive messages. I will start from the second message, just anything, which is all passed to process 2. But if we receive message of type exit, it's a tuple of 3 elements, keyword exit, process ID, and the exit reason. Instead of terminating, we restart process 2 and continue. So here we have the situation, we have a process which observes another one, traps its exits, and restarts it again. It's a very, very primitive example of what is called supervision in Erlang world, when one process basically supervises and monitors another one. Without such an ability, we'll obviously could get to the situation when one crash will kill basically the whole system as a chain of subsequent linked exits. And here, if certain process has trap exit set to true, it's a point where crash propagation stops, and we can make some decisions, do something to recover, restart, do some clever job. Next, processes are good, but still it's two-level construct to create something more or less big. What we need, usually, we need some kind of worker which can receive messages, which get already some semantics, not just messages, usually some requests. It should be able to respond to these messages. It should be able to maintain some state in a consistent way, and should be easily usable. Theoretically, and if this talk would be longer, I would demonstrate how to, in several steps, build such a construct just out of plain processes. But we have not that much time, so I will skip these intermediate things and immediately show how generic server works. So it's something which basically internally is a process. You can receive synchronous or asynchronous requests to it. It provides synchronized access to state. State consistency is guaranteed in the sense that if a generic server terminates, all its state is discarded and becomes unavailable. It means we'll never get into some data which is probably a little bit broken or wrong. That's what I say, discard state and crash. Internally, it's just a process, so it has all properties of usual process. You can link generic servers to other processes. It can trap exits and receive messages about crashes. And logically, it can be seen as a very, very small microservice which helps you structure your application. Here, I'm introducing another very simple concept called behavior. Behavior, nothing else than, in case of Erlang, Erlang has modules and Clojure has namespaces. Basically, if I have a module with several functions with predefined, with well-agreed names, I say I define the behavior. In case of Clojure, it's the same. We may have a namespace with several functions with predefined name. In this case, I have 3 functions. One function is called init. It's required. It must be in any generic server behavior. Handle call, handle cast, and there are a couple of others which I skipped for simplicity, are optional and are required only in case I would like to achieve something. On a lower level, it's possible to define behavior simply by implementing iGen server protocol, but it usually leads to slightly more verbose code, and not, to my taste, it's not as convenient as using predefined functions and namespaces. So here is our first simple generic server. What is important? We have an init callback. All these callbacks are called, let's say, by the framework. Init is responsible for a very simple basic operation. It receives some parameters. In this example, it receives no parameters, and it has to return initial state of the process if these parameters are valid. So here we say that we're fine. We return initial state, which is an empty map, and we can go ahead. Then second callback is called handle call. This callback is invoked every time someone wants to synchronously access our generic service. First parameter is a message. Second, we skip for now. And the third is very important, is this is our state. So with every request, we receive a state. We handle this request, and we're responsible for returning new state if we want to modify it. Or in the simple example, we return the same state without any change. Here, we match on message. We support only one type of message, which is add, which adds 2 numbers. So it's our very simple generic server, which adds numbers. And we reply with our result, A1, A2 plus, and we return the same state. As before, state is not changed. Then for convention, we create a kind of wrapper function, just regular Clojure function. We add another parameter. First one, it's a process ID of the server. We have to address it somehow. And we use a GS generic service call function to pass the request to the server. And finally, our example, we start generic server, and invoke add function with 2 parameters and expect that it will work properly. In case we send a wrong message, our generic server will crash, and obviously its internal state will get discarded. Here we have slightly more advanced example where I show how to deal with internal server state. In addition to add message, which is same, almost same, we added another one, which is called count, which is supposed to return how many times this number, how many times our generic server was called for adding something. Imagine we want to charge our customer for adding numbers. In the init method, our initial state is already more advanced. It's not just empty map. It's a map with count property with initial value 0. Our add function is almost the same, besides that we modify the state. We receive, you see as a third parameter of handle call function, we receive initial state, and then we do update in state, increment count. Very simple. Now, with every call to add, our counter gets incremented. And we have another message called count, which just returns count field, count attributes of our state, and return state unmodified. We have wrappers, we have add, and we have get count, and we use them. Here I use the chance to demonstrate another thing, that it's possible to register our generic servers under some names. So here my service is a ID. Our instance of our generic service, a process associated with it, gets registered, and we can use it to reference without knowing process ID directly. If our service will crash, our generic server will crash, of course this registration will be discarded. Next, supervisors. Previous example was good, but I can maybe scroll for a second a bit, but it still looks a bit strange where we should register, where we should start our services, at which point, and more important, what shall we do if our process terminates out of some reason. It gets unregistered and our server will be gone forever. In this case, we have to have a special party who is responsible for starting and maybe restarting our servers. So for this we have supervisors. They're responsible for starting generic servers, and by the way, other supervisors. And supervisors are responsible for restarting processes in case of crash. It's a special generic server, so it has all the properties of generic server. Internally, it has a more or less declarative start specification. I will show an example later with more details, but in fact, it's nothing else than a list of generic servers that have to be started and managed by the given supervisor. It initially starts its children according to start specification and restarts them in case of crash, in case of any problems. It supports so-called restart strategies. Here I specified one for one, one for all, one for the rest. This is a very important story, because actually it's very often they may have several generic servers which are related to each other, that have something in common to be somehow synchronized. And what is very important to know that if one of them crashes, another may get restarted or not restarted, depending on what you program. So we have 3 strategies. They specify how neighbor processes are managed. In case of one for one, it's the simplest case. Our supervisor will just restart the process, the servers, which has crashed. It's a simple case. One for all means if one of these processes crashed, supervisor will kill all its neighbors and restart them all together. It means we're sure that even if one participant of our supervisor crashed, got restarted, it means received new state, started from scratch. All its neighbors have to do the same. This will guarantee that they are synchronized and can cooperate together properly. And one for rest, it's basically something in between. It means that it's almost like one for all. We restart others, but only those others which started after the crashing service. Usually you start services in the order of their dependence, and obviously if there are processes which started somewhere before the crashed one, they're not dependent on it, and then there is no need to restart. It's a sort of optimization to avoid unnecessary restarts. As I mentioned, it's absolutely normal practice to have other supervisors as a child of another. So, in the end, you have something which is called supervision tree. I borrowed these pictures from some open source Erlang book. Here, green cycles are supervisors, and blue cycles are workers or generic servers, some processes which are really in charge of doing something useful. If you have certain experience and feeling for this, it's absolutely normal practice when you design your whole application as a big supervision tree with many elements, but that can be 10, 20, 50 of them. Each small server is responsible for its own small part. They coordinate, and supervisors manage them and restart in case of something gets wrong, discard state, and let things move ahead. Here, before, all our examples were basically fake, and here I decided to make a snippet. It's still very much reduced just to fit on the screen. It's a small snippet from real-life code. It shows the supervision specification, child specification. You see, we have 1, 2, 3, how many? 7, I think, children. And some of them are generic services, like you see, service responsible for configuration. We have an HTTP server. We have a database connection server. Some of these children are supervisors itself. For example, we have a session supervisor, which holds session processes, which are, it's definitely some kind of client-server architecture, and the session supervisor is in charge of holding user sessions. Why it's a separate supervisor? The reason is very simple. This one is one for all. It means if one of these services will crash, all others will get restarted. But user session crash is a normal operation, like we received the incorrect request from the client side, and we want to crash our session. So obviously it has to have impact only on the user application, the client application. So we move them to a separate supervisor. Means user session will crash. Maybe, it depends if we do it cleverly, it will even crash and restart, reconnect, and recover our communication between client and server, but all other participants of the application will never notice it. So it's kind of normal practice to have supervisors for such, let's say, more transient entities like sessions. So this is our real life supervisor. And now I will, 30 minutes, we have 40. I will go again back to some generic words, first of all to conclusions. So we internally as a company, we're a consultancy company based in Germany. We are from south, from Stuttgart. We find it very useful. Actually, we're developing a big system for, let me put it, so one of the major German car producers from the southern part of Germany, put it that way. And this project is pretty far now. And actually the story behind OTP-like is like I started. Our first version was built just on plain core.async. It did the job, but it required a lot of attention, a lot of let's say, policy and discipline to make it proper, stable, reliable, and clean. So we started to think, okay, what can we improve? we decide, okay, we take our past experience from Erlang and moved it to our world. Currently, OTP-like is used in 2 major projects, as far as I know, projects. That's our automotive project, and this automotive project in the field of engineering systems. Actually, it's a software which is used by engineers who could design cars. As far as I know, there is another project here in Berlin. In the banking, there is some banking, financial technology, fintech, or what is the buzzword for that, startup here. They're using it as well. So what are the next steps? What we're moving? We still have plenty of things to do. We want to get it running in the Clojure script. And actually, we're pretty close to that point. I had a dream that I could even demonstrate it here, but unfortunately, we had some other more urgent things, and we're not able to do it. But I guess sooner or later, it will be there. Because actually, I want to have similar structures inside the browser, which is able to talk with the server, and here remoting and distribution comes in. We're not sure if we want to create a full-sized remoting like in Erlang. Perhaps it will be a limited remoting which will only work between Clojure script version of OTP-like and Clojure version. So it's a nice way for client-server communication, and you can build other things on top of it. It's nice, and for example, connection crashes, it gets restarted, state gets recovered, and you can make very, very interesting things out of it. We want to support so-called applications. Applications is a kind of higher-level unit in Erlang where you group basically a supervision tree into a more or less independent entity which can be combined together. This we don't have it, unfortunately. Distribution was mentioned by me. I think something will be there, but it's still open question. We want a more advanced process registry. Right now, our process registry is something which associates some conventional names, convenient names with process IDs. It works. Now we have it in the state as it is in real life Erlang. But there is such a thing as gproc. It's an external library for Erlang, which provides much more advanced, much more sophisticated ways to register processes. For example, it's possible to register several processes under the same name, if you do it properly. And then you can send a message to the group of processes. It's a very nice way to create publish-subscribe architecture. So I want to inform every process which registered itself under some predefined name. We have, of course, flexibility and nice chance to add additional things or modify a little bit here and there semantics of Erlang. We don't have to struggle for compatibility as Erlang people do. Actually, I skipped it all in the presentation, but here and there we have some nice additional gimmicks. One of the examples is our timeout handler in the receive block. Instead of time in milliseconds, you can pass a channel, and this timeout will fire once this channel gets closed. You can do very nice interoperability between OTP-like processes and still conventional plain core.async code. A little bit of information. Project on the GitHub. Welcome. Right now it's still quite simple, but it's very reliable. We have, I think, several hundreds of very thoroughly done test cases. Thank you for my colleague Simon. He did a great job with testing, and we are pretty sure that in most cases it works well. If anyone is interested, curious about Erlang OTP, there is a very good open source book, learnusesomeerlang.com. And actually few pictures in the presentation are taken from this book. I would encourage everyone at least to take a look. You know, if you learn language, it's not necessarily you'll program it, but you may use some ideas or some insights from that. You can subscribe to my Twitter, suprematicAV. I'm not a very social person. I don't tweet too often, but at least some release announcements and other things are there. Our company is Suprematic.net. If you want, you can visit us or apply for a job. We have some openings. Actually, they were in the this job letter, job announcement for the conference. Or visit us in Stuttgart. We can have a beer. One more thing I mentioned, maybe it's more relevant to the previous slide. There are several things which are also supported but are not mentioned in the presentation, just for the simplicity and to make it slightly shorter. But we have monitoring as well to linking. It's a very important thing, and we have monitors fully supported. We have timers, so we can do some delays, some regular events and so on. And made quite many different things around, minor things, copied from Erlang OTP here and there for our convenience. That was it. It's 36 minutes out of 40. And now we have 4 minutes left for questions if you have any.